This is lecture 4G. We've previously learned how to determine the number of moles of a chemical if you're able to measure the mass of that chemical on a balance in a lab room. The way we convert a given mass of a chemical into moles is by using the molar mass of the particular material, probably the most fundamental conversion we do in chemistry. But another type of conversion we're going to need to be able to do is to be able to convert solution data into moles. And we're going to talk today about how you get moles from solution data. Let's do an example. Let's say we want to determine how many moles of the solute potassium carbonate there are in 275 milliliters of a 0.300 molar potassium carbonate solution. So when you're trying to calculate moles of a particular chemical that happen to be dissolved in a solution, and you know its concentration, you're going to go to the definition of that concentration unit. Molarity, capital M, is abbreviated by quantity over volume. Quantity is N, volume is V. And the quantity, the N value in this equation, is measured in the units of moles. So if we want to calculate the number of moles of the dissolved solute, that's N in this equation. We would just multiply each side of the equation by V, and so that means the number of moles of the dissolved solute in any solution will always be its molarity multiplied by its volume. And that's a really easy calculation to do, and that's essentially why they invented the concentration unit of molarity. If you want to determine the number of moles, which is a measure of how many particles there are dissolved in the solution, all you have to do is multiply the molarity times the volume. And it's easy to make volume measurements of solutions in chemistry. That's why we have beakers and pipettes and burettes and graduated cylinders. So the key for today, when we talk about solution data and doing conversions from solution data into moles and moles into solution data, is going to be the number of moles of the dissolved solute are just going to equal molarity times volume. And if you wound up going to Mission Viejo High School, then you should never miss this. So let's try this problem. The molarity is 0.300. If I want to see the units work out, though, the capital M in 0.300 M is just the abbreviation for the unit of molarity. Molarity is actually moles of solute per liter of solution. So when I do the calculation multiplying the molarity times the volume, I'm not going to write 0.300 capital M because that's not going to cancel out. I have to write explicitly what molarity is. 0.300 moles of our solute potassium carbonate per liter of solution. Now when I multiply by the volume, if I want those units to cancel out, I know I can't multiply by 275 milliliters. I have to move the decimal point 3 places to the left, convert that to 0.275 liters. And now when I multiply these together, liters of solution cancel out, and we will calculate the number of moles of the potassium carbonate that have to be in this particular solution. So a 3 significant figure number, 0.0, beginning zeros don't count, 325 moles of K2CO3. So this tells us how many moles of the crystalline substance potassium carbonate you would have had to dissolve into this solution in order to make a solution whose molarity is 0.300 molar if you have 275 milliliters of it. When potassium carbonate dissolves in water, though, however, it's an electrolyte and it dissociates into ions. So there's going to be some potassium ions floating around in the solution and some carbonate ions floating around the solution. And what we're going to need to be able to do is, once it's in solution, be able to determine the number of moles of the potassium ions and the moles of the carbonate ions. So let's find the moles of each of the ions in the 0.300 molar potassium carbonate solution. And this is very similar to a concept we've done before. If you know what the molarity, for example, of a compound is, you can predict the molarity of the individual ions when it dissolves just based upon how many ions are in the formula. And the same thing works for moles. If we know there are 0.0825 moles of potassium carbonate that have been dissolved into a solution, and there's 2 potassiums in the formula unit, K2CO3, then the number of moles of potassium have to be 2 times this number. So if you multiply that by 2, that's going to give you the number of moles of potassium ions in the solution. And because there's only 1 carbonate in the formula of the compound, every time 1 formula unit dissolves, you only release 1 carbonate. So if you multiply the moles of the dissolved salt by 1, you'll get the number of moles of carbonate in the solution. So with those couple of things in mind, let's do some applications. I want to talk about the mixing of 2 solutions together and see if we can determine what the molarities are and what the moles are of each of the different components in this particular solution. So we're going to take 10.0 milliliters of 0.450 molar barium chloride and mix it with 20.0 milliliters of 0.300 molar potassium sulfate. And I'm going to ask you a series of questions about the mixed solution. A, we're going to try to find the moles of each ion present in this solution. So anytime you mix solutions together, if you have a corresponding volume and molarity, and we do that for the barium chloride, we can use this molarity and this volume to calculate the moles of barium chloride. If you know our corresponding volume and molarity for the potassium sulfate, you can use this molarity and this volume to calculate the moles of the potassium sulfate. So we have to do two separate calculations, but to calculate the moles of each solute, it's still going to be molarity times volume, but it has to be the corresponding molarity and volumes. So the 10.0 milliliters of our first solution was 0.450 molar barium chloride. If we multiply those numbers together, that's going to give us the moles of the barium chloride. So the molarity of the barium chloride is 0.450 moles of BaCl2 per liter. What was the volume of the solution that had that molarity? 10 milliliters. Switch to liters, it's 0.0100 liters. Liters cancel out, so we're technically calculating how many moles of barium chloride there were in that original 10 milliliters, but then if we mix it with a bunch of other stuff that doesn't have barium or chloride, it's going to be the same number of moles. So the number of moles in that original 10 milliliters is going to be the number of moles of barium chloride when the two solutions have been mixed together. That comes out 0.00450 moles of barium chloride. We'll do the same thing with the potassium sulfate. We know that we had 20 milliliters of 0.300 molar potassium sulfate to start with. So I'm going to multiply that molarity times volume to calculate how many moles of potassium sulfate there are in that original 20 milliliters. So let me say about this one first, though, before we go on. So if we know it's 0.00450 moles of barium chloride, then like we just talked about, by inspection, there's one barium in the formula. So 1 multiplied by 0.00450 will give us the moles of the barium ions. But there's 2 chloride ions in the formula, so 2 multiplied by 0.00450 will give us the moles of the chloride ions. So I've put those two answers in yellow. That's actually what the question is asking. What are the moles of each ion in the solution? So molarity times volume tells us the moles of the dissolved salt in the solution, and then as it dissociates, we can calculate the moles of the individual ions. Now on to the potassium sulfate component. It was 0.300 moles of potassium sulfate per liter, and we had 20 milliliters of that solution, so converted to liters, that would be 0.0200 liters. Liters cancel out, and that's going to give us the number of moles of potassium sulfate that were in that original 20 milliliter solution. If we mix it with 10 milliliters of something else, though, we're not adding any more of it, so there's still going to be 0.00600 moles of potassium sulfate once the 10 and the 20 milliliters have been mixed together to make a total volume of 30. So if we know there's 0.00600 moles of potassium sulfate, now by inspection, as it dissociates, we can tell that there's 2 potassium ions in the formula. So therefore, the moles of potassium ions are going to be 0.00600 times 2, or 0.0120 moles of potassium ions. And there's 1 sulfate in the formula, not 4 of them. SO4 is a sulfate. There's 1 sulfate in the formula, so 0.00600 times 1 would give me 0.00600 moles of sulfate ions. So the yellow answers in this page are the answers to part A. What are the moles of each of the individual ions in this particular solution? Let me give you a part B. Find the moles of each ion after any reaction. So now when you mix solutions together, sometimes a chemical reaction takes place. If we look at what may be reacting, we're mixing together barium chloride and potassium sulfate. Those are 2 compounds. What type of reactions did we learn about when 2 compounds react? Those would be exchange reactions. They either form a precipitate or a water or a gas. So if we look at our answers from part A, we add a certain number of moles of barium ions and a certain moles of chloride ions from the first solution that was mixed, and then a certain moles of potassium and a certain moles of sulfate from the second solution. These are now all in the same beaker. And essentially, when you do an exchange reaction, what do? You switch partners. So what you should do is you should imagine maybe the barium going with the sulfate and the potassium going with the chloride, and what you're looking for is either a precipitate or water or a gas. Potassium and chloride can't be a precipitate because of the solubility rule. Potassium ions or alkali metal ions never precipitate with anything, but the barium with the sulfate will form a precipitate. Sulfate never precipitates with anything except with silver, mercury, calcium, strontium, and barium. So when they say if a reaction occurs, there is a reaction that's happening when you mix these two solutions together. The barium ions from the first solution will eventually bump into the sulfate ions from the second solution, and they will form a precipitate barium sulfate. So that means our 0.00450 moles of barium ions is not actually correct because some of them are going to precipitate out of the solution. And the 0.00600 moles of sulfate ions is not a correct number because some of those are going to precipitate out of the solution. This number is perfectly fine because the potassium ions aren't being changed. This number is perfectly fine because the chloride ions aren't being affected or aren't being changed. So if we want to determine what the barium and sulfate moles will be now after a reaction occurs, we're going to do an initial moles, change moles, and final moles table. So what do we have in the solution? We have 0.00450 moles of barium ions and 0.00600 moles of sulfate ions, nothing else. Barium and sulfate react in a 1-to-1 ratio. So which one of these two reactants is going to be the limiting reactant? It's easy if it's a 1-to-1 ratio, it always has to be the smallest one. So 0.00450 moles of barium will react with 0.00450 moles of sulfate to produce 1-to-1-to-1 ratio, 0.00450 moles of barium sulfate. Remember what we said about this change line when we're doing our stoichiometry. What's this ratio? 1-to-1-to-1. Why is that? Because the coefficients in the balanced equation are 1-to-1-to-1. The coefficients in the balanced equation are always going to equal the exact same ratio as the amount of chemical change that takes place. So if we subtract now, there aren't going to be any barium ions left in the solution. You'll have a little bit of sulfate ions left, 0.00150. And if you want to know how much solid is going to be sitting at the bottom of that container, there's going to be 0.00450 moles of precipitated barium sulfate. So to answer the question, we're going to have no moles of barium in the solution, 0.00150 moles of sulfate left in the solution after the precipitate. And if you remember, the potassium ions and the chloride ions didn't get affected at all, so their values are going to stay the same. We'll still have 0.00900 moles of chloride ions in the solution, and we'll still have 0.0120 moles of potassium ions in the solution. Let's try part C. Find the final molarities of each of the ions in the solution. Molarities are moles divided by liters. So in part B, we have the number of moles of each of the substances in the solution after the precipitation reaction occurred. So if we know the number of moles of each, to calculate molarities, you just take moles and divide it by the volume. So now you have to realize that if you're mixing together 10 milliliters of one solution with 20 milliliters of another, your graduated cylinder is going to show a volume of 30 milliliters. That's the final volume of this mixed solution. So to get the concentrations of each of these ions, you're going to take their corresponding moles and divide it by the volume of 30.0 milliliters converted to liters. So for the barium, it would be 0 moles divided by 0.0300 liters, and that one comes out pretty easy. For the sulfate, it's going to be 0.00150 moles of sulfate divided by 0.0300 liters. We'll get a 3 significant figure answer for this. That comes out 0.0, then 500 molar sulfate. For the final ions, chloride, 0.00900 moles divided by 0.0300 liters, both numbers 3 significant figures. Your answer will be 3 significant figures. That comes out 0.300 molar in chloride ions. And we do the same thing for the potassium. Take the moles of potassium divided by the volume. Both of these numbers are 3 significant figures, and so the molarity is going to wind up coming out 3 significant figures, 0.400 molar. Let's try one more example of this, and if you want to, for each part A, B, and C, pause it and try to do the calculation on your own, that would be perfectly fine. Second problem then, let's say 20.0 milliliters of 0.350 molar hydrochloric acid are mixed with 30.0 milliliters of 0.250 molar sodium hydroxide. And the first thing we're going to try to do is find the number of moles of each ion in this solution. You ever want to calculate the number of moles of a dissolved solute in a solution? It's always going to be Mission Viejo, molarity times volume. So for each of the two components, first for the HCl, I know it's a molarity when we had 20 milliliters of it. So I'm going to multiply the molarity of the HCl, 0.350 moles per liter, by the volume of that HCl solution, switch to liters, 0.0200 liters. Liters cancel out. There's the moles of the HCl that must be in that original 20 milliliters. And then when you mix it with 30 milliliters of something else, that's not going to affect it. So that's going to be the actual moles when the two solutions have been mixed together. Because HCl is a strong acid and it 100% ionizes, the moles of hydrogen ions and the moles of chloride ions will each be 0.00700 times 1, because there's only one hydrogen and only one chloride in the formula. So these will be the moles of the two ions that are created with the complete ionization of 0.00700 moles of HCl. Now for the other component, the sodium hydroxide. When we had our original 30 milliliters of it, its molarity was 0.250 molar. So if I multiply molarity times volume, I'm going to get the moles of the sodium hydroxide. So 0.250 moles per liter is how I write molarity out. Multiply it by the volume converted to liters, 0.0300 liters, and that's going to give us 0.00750 moles of sodium hydroxide from that original 30 milliliters. And then when we mix it with 20 milliliters of other material, it's still going to be that same number of moles of sodium hydroxide. This is a soluble ionic compound. It completely dissociates, and there's only one sodium and one hydroxide in the formula. So if you multiply 0.00750 by 1, you're going to get the number of moles of sodium ions and the number of moles of hydroxide ions that are in this solution. Let's go to part B. Find the moles of each ion after any reaction. So here we have two compounds being mixed together, two soluble compounds being mixed together, two compounds reacting. You would imagine an exchange reaction. So you switch the partners and you look for a precipitate, water, or a gas. So our answers from part A are given here. The hydrogens and chlorides come from the HCl and the sodiums and hydroxides from the NaOH. And if we switch the partners, we would mean the hydrogen from the first solution would mix with the hydroxides from the second, and the sodiums from the second would mix with the chlorides from the first. Sodium with chloride would have to be soluble because alkali metal ions never precipitate with anything, but hydrogens and hydroxides will combine to form water, and if you form a precipitate, water, or a gas, that's the chemical change that's occurring. So these are the two ions out of the four that are reacting with each other, and they're forming a water molecule. And we need to figure out how much of the hydrogens and how much of the hydroxides react away. So we'll do an initial, change, and final moles table. So the sodium ion moles will never change, and the chloride ion moles will never change. They're not undergoing any chemical reaction, but the hydrogens and hydroxides will. So we had 0.00700 moles of hydrogen ions, 0.00750 moles of hydroxide ions. The hydrogen ions are the lesser of the two. It's a 1-to-1 ratio, so the lesser one will always be the limiting reactant if it's a 1-to-1 ratio. So 0.00700 moles of hydrogen will react with 0.00700 moles of hydroxide. Has to be a 1-to-1 ratio to match the coefficients in the balanced equation. And you're going to form 0.00700 moles of water, 1-to-1-to-1 ratio. Subtract down, we'll have no hydrogen ions left after the reaction occurs, a very small amount, 0.00050 moles of hydroxides, and we will have formed 0.00700 moles of extra water besides all the water that was already in the solution anyway, because anytime they say a certain molarity of HCl or a certain molarity of NaOH, it just means some of the HCl and some of the NaOH is dissolved in oodles of water. And so here we've just calculated how much extra water is going to be formed besides all the water that was actually in there originally. So therefore, the moles of hydrogen ions left in the solution is 0. The moles of hydroxides get reduced to 0.00050, and the sodium ions and the chloride ions remain unchanged, 0.00700 moles of chloride and 0.00750 moles of sodium ions. Part C. Find the final molarities of each ion in the solution. So from part B, if we know how many moles there are of each of the ions in the solution, anytime you mix solutions together, unless you're told otherwise, you can assume the volumes are additive. So if you mix 20 milliliters and 30 milliliters, you're going to make 50 milliliters of solution. So to convert moles into molarity, you just take the moles and divide them by the volume. So for the hydrogen ions, it's 0 moles divided by the sum, 0.0500 liters. For the hydroxides, it's 0.00050 divided by the sum, 0.0500 liters. Notice the moles of hydroxide are only a 2 significant figure number here, so that means your molarity is going to need to be rounded to only 2 significant figures, 0.010 molar. Then for the chloride ions, it's 0.00700 moles divided by the volume, both 3 significant figure numbers. So in this case, the answer will come out 3 significant figures, 0.140 molar. And the same thing for the sodium, take its moles, 0.00750 moles, divided by the combined volume in liters, and that'll be a 3 significant figure answer as well. That comes out 0.150 molar in sodium ions. Let me give you one final part to this problem, part D. Let's find the mass of water that was produced by this reaction. So not the amount of water that was already in the solution initially, it's how much water was produced. So if you look back at our problem where we did a initial change in final moles table, we deduced that when this reaction occurs, you must be producing right here 0.00700 moles of water. So if they want to know the mass of water that's produced, you just take the 0.00700 moles, and the way we switch moles into grams or grams into moles is the molar mass of the particular substance. So you figure out water's molar mass from the periodic table and you arrange it with the mole fraction part of it on the bottom and the gram fraction of that equality on the top. So the moles cancel out, and this turns out to be 0.126 grams of water were actually created when these solutions were mixed. One final type of calculation I'd like you to be able to do when you're dealing with solution chemistry is the concept of doing dilutions. And there's a simple way to actually do dilution calculations. And it really comes from the idea of what really changes when you dilute a solution or what you're doing to dilute a solution. When you dilute something, all you're doing is adding extra solvent. So if you have, I don't know what, like a Coke at McDonald's or something, and you pour a whole bunch of water into there, the amount of sugar that was in that Coke is just now mixed with more water. But the amount of sugar, which is a solute, doesn't change. And so that's important to understand. When a solution is diluted, you only add solvent. That means the amount of solute does not change. If this is a flask that has an orange solvent and those little black dots are the solutes, and I think there's 14 of them in there, so maybe there's 14 solute molecules in there. What if I add a whole bunch more solvent to this? So now it's really full. Well, count the number of dots. What do you think it's going to be? It's going to still be 14. I'm only adding orange solvent. I'm not adding any more solute. That's what diluting is. You just add more solvent so that now the solute particles are spread out more. If those were sugar molecules, the solution on the left, if it touched your tongue, it would seem really sugary because there's lots of sugar molecules touching your tongue with each bit of solution. But the solution on the right, because the sugar molecules are spread out, each drop of liquid that goes onto your tongue, they won't have as many sugar molecules. It won't seem quite as sweet. So the major concept here is the moles of solute remain unchanged when you dilute a solution. So we can say that the moles of solute in our original concentrated solution has to exactly equal the moles of solute in our newly created diluted solution. That's always true. So the first thing we learned today, how do you calculate the number of moles of solute in a solution? You multiply molarity times volume. So for our original concentrated solution, the molarity of that concentrated solution times the volume of that concentrated solution is the moles of solute in the concentrated solution. On the right, the moles of solute in the diluted solution will be the molarity of the diluted solution times the volume of the diluted solution. So therefore, we can write an algebraic equation relating these two solutions, the molarity of the concentrated solution, MC, multiplied by the molarity, the volume of the concentrated solution, VC, must equal the molarity of the diluted solution, MD, multiplied by the volume of the diluted solution, VD, which is unfortunate. Now, if you want to do this M1 V1 equals M2 V2, I have no problem at all. That works perfectly fine. But I use the C's and the D's as the subscript just to visualize that this is a concentrated solution and a dilute solution, and they're related to each other. Let's try an example. Let's calculate the volume of 6.00 molar ammonia needed to prepare 250 milliliters of a 0.100 molar ammonia solution. So this is a typical dilution problem. You want to know how much of this 6 molar ammonia, which is a high concentration, that's the concentrated solution. is needed to prepare 250 milliliters of 0.1 molar ammonia, which is more diluted. So the way you do this is you're not making the ammonia react with anything. You're just going to add more water to it. So it doesn't have 6 moles per liter. It goes all the way down to only 0.1 moles per liter. This is a dilution problem. It's important to recognize this equation, this M1V1 equals M2V2, only relates to when you add solvent and you dilute a particular chemical. If a chemical reaction is taking place, this particular equation does not work. So we can use the dilution equation because we're just diluting the ammonia solution. Let's see if we can identify each of the variables. The molarity of the concentrated solution is whichever is your higher concentration of the two. That's the 6 molar. Now, what's the corresponding volume to that? It says calculate the volume of 6 molar ammonia. So that means that's the variable we don't know. The diluted solution is going to have a lower molarity, so M sub D is going to be the 0.100 molar, and there's a volume associated with that. It says 250 milliliters of 0.100 molar, so I can put that here. So we're trying to solve for V sub C. So if you take your top equation here and just isolate the V sub C, then we're going to know how we multiply and divide all the variables together in order to get our answer. So I'm just going to plug in the molarity of the diluted solution, 0.100 molar, the volume of the diluted solution, 250 milliliters, and divide it by the molarity of the concentrated solution, 6.00 molar. Now, when you use the definition of molarity, molarity equals N over V, in that case, you have to use the molarity as moles per liter. The N value has to be moles, the volume value has to be liters. But when you use the dilution equation, you don't have to do that. This is what we call a comparator equation. It has the same variables on the left side as it is on the right side. They're just under different circumstances. This is when they were concentrated. This is when they were diluted. If you ever have a comparator equation where the variables are the same on the left and the right side, the particular units don't have to be anything in specific. It's just that whatever units you use for M on this side, you have to use the same units for M on this side. Whatever units you use for volume on this side, you have to use the same units on that side. So if I leave my volume in milliliters, that's fine. It just means my answer will come out in milliliters. If I write my molarities just as capital M instead of moles per liter, that's fine because what do the M's do? They cancel out. If I rewrote it as moles per liter over moles per liter, they would cancel out as well. So it actually simplifies the problem to a small extent. So the molarities cancel out here, and if I use my volume in milliliters, I'll get an answer in milliliters, 4.17. If I would have switched that to liters, then I would just have an answer in liters, which would still be correct. It would just be 0.00417 liters. So the significance of this problem just means that if you want to make 250 milliliters of 0.1 molar ammonia, what you need to do is you need to take 4.17 milliliters of the 6 molar, really small amount of it, and then put it in a flask and dilute it till the final volume gets to 250 milliliters, and then you'll have the concentration reduced all the way down to 0.100 molar. Let's try one other calculation, and I'll show you why you're going to get this one wrong. Calculate the volume of water that must be added to 5.00 milliliters of concentrated hydrochloric acid, whose molarity is 12.1 molar, to make the acid 3.00 molar. So this one's definitely a dilution calculation because they're saying how much solvent do you have to add so that you change the molarity of the HCl from 12 to 3. So I'm going to use my dilution equation, and I'm going to try to identify each of the variables that I know so that I know which one I have to solve for. So the molarity of the concentrated solution is going to be whichever concentration value is higher, and 12.1 is higher than 3, so that's 12.1 molar. And it says added to 5, so it says 5.00 milliliters of the concentrated hydrochloric acid, so they're telling you its volume. The molarity of the diluted solution must be 3.00 molar. It's the only other molarity in there, and it's the lower one, but they don't tell you the volume of the diluted solution, so that's what you solve for. So if you want to solve for the volume of the diluted solution, which is right here, I'm going to move the M sub D over to the other side of the equation, and I'm going to plug the numbers into our dilution equation. So it's going to be 12.1 molar multiplied by 5.00 milliliters divided by 3.00 molar, and the molars will just cancel out. I'll get my answer in milliliters, and this comes out 20.2 milliliters. If you think you're done, you're wrong, because that's not the answer to the question. What is it that you've just calculated? That 20.2 is the volume of the diluted solution. Read the first part of the problem again. Calculate the volume of water that must be added. So how are you going to figure that out? Well, you started with 5 milliliters of the concentrated acid. You made the volume go up to 20.2. So how much water do you have to add? You have to subtract 5.00 from that, and that'll tell you the difference. That'll tell you how much water needed to be added to make this solution, which comes out 15.2 milliliters. This is the answer to the question. This is the amount of water that must be added to make that solution.